Welcome, listeners, to another engaging episode of In Depth with Academia. I'm Richard Price, your host, and I'm thrilled to dive into another fascinating piece of academic research with you today. As always, our goal is to make complex ideas accessible and explore how they might impact our lives. Today, we're examining a paper by Prabhat Ranjan, a remarkable researcher whose work takes us back in time and yet is astonishingly relevant today. The paper titled Helically Linked Mirror Arrangement was originally a PhD thesis from 1986, yet it tackles questions that are alive and kicking in the world of energy research, particularly the quest for sustainable and efficient fusion energy. Now, fusion energy, that's a big promise, isn't it? Imagine energy like that of the stars, a near limitless supply, clean and safe. But while Tokamak devices, which are at the forefront in fusion research, are getting closer to achieving break-even for fusion energy, they're not without their challenges. Technical and economic hurdles, the pulse nature of their operation, and their immense size. These complexities mean there's still room to explore alternative approaches. This paper suggests one such alternative scheme. The core problem it addresses: how to effectively link mirror sections in a fusion reactor to combine the benefits of both toroidal and mirror devices without the downsides of each. This question is significant. It's an ambition to blend the continuous operation and stability of toroidal devices with the simplicity and high beta, meaning plasma pressure to magnetic pressure ratio, of mirror devices. Now let's break this down. Essentially, what Ranjan proposes is a fusion device that employs a helically linked mirror arrangement. Imagine a helix like a spiral staircase where the plasma is held tight as it navigates through this structure. The key here is that instead of the plasma racing out of the ends of a mirror machine, the helix keeps it from straying, leveraging rotational dynamism similar to that of a stellarator or helical device. But how does it work exactly? Well, here's the fascinating bit. He uses 3 straight mirror sections, each linked by 3 helical sections. Envision this. It's like taking magnetic fields, usually in straight lines or simple loops, and twisting them through elegant mathematical gymnastics. These helical segments bring rotational transformation, vital for confining particles more effectively. I mean, it's wild, right? It reminds me of a conversation with a friend of mine who once compared it to a roller coaster. You know how a complex track can harness momentum to keep the carts moving? Here it's a similar idea with these magnetic fields guiding and holding plasma particles in place so they don't escape too easily. Through theoretical analyses complemented by numerical simulations, Ranjan's paper reveals that this arrangement can indeed confine passing particles well. Of course, there are some challenges, like the loss of some trapped particles in those helical sections. They get lost quickly, but being a scientist at heart, Ranjan doesn't shy away from these details. It's about bringing awareness and a basis upon which others might innovate further. Furthermore, Ranjan estimates the rotational transform. This geeky-sounding term basically refers to how much the magnetic fields twist along the path. A full 360 degrees would be one complete twist, so imagine having like 310 degrees. Not quite a full turn, but enough to keep a steady configuration influencing those particles. But let's not forget that academic research is a leap into the unknown, and nothing here is endorsed as the ultimate truth. It's about exploration. What does this paper mean for you, the listener? It shows that innovation, whether last year or over 3 decades ago, fuels our quest for sustainable fusion energy. And it's as timely as ever in the race against climate change. In wrapping up, we see that this paper does more than just present equations and theory. It challenges us to rethink and remodel methods once considered. Science isn't static. Each paper, each discovery, each thesis is a stepping stone to what might be the next breakthrough. Thank you all for tuning in to In Depth with Academia. As always, keep questioning, keep exploring, and stay curious. I'm Richard Price, and I'll catch you next time with more insights from the world of academia. Exciting, isn't it? Until then, take care and keep wondering.